Good evening, and on behalf of St. Sebastian's, welcome to the third installment of our four-part faculty seminar series, The Wave-Particle Duel of Light. Tonight, we are joined by the Chair of the Science Department, Mr. David Wilbur. My name is Mike Melly, and I am the Director of Alumni Programs at St. Sebastian's. It can be said that physics is a contact sport. For anyone who knows Dave Wilbur, it is not surprising at all that he is a physics teacher. For those of us who have not attended Mr. Wilbur's class, a testimony from his former student, Will Bernard, from the class of 2012, and like Mr. Wilbur, a graduate of WPI, says it all, and I quote, "Mr. Wilbur teaches physics and how to be your best self. He is the greatest mentor I have ever known, and his guidance formed the foundation of my entire career and the man I am today. Thank you for constantly pushing me to be a better student, teammate, and leader." Will's comment encapsulates the impact that Dave Wilbur has had on so many St. Sebastian's alumni over the years. For those of you who are new to Zoom, I would encourage you to look in the upper right-hand corner of your screen and click on the button that says Speaker View. Now you should only be seeing me, but shortly you will see Dave. Throughout the presentation, we will be sharing slides to illustrate this fascinating topic, and the prepared remarks will be followed by a Q&A session. Feel free to contact me in the chat session during the presentation, and I will call on you when the time comes. Dave Wilbur was born in the foreign country of Minot, North Dakota, and raised as an Air Force brat in Alabama, Arizona, Colorado, Maine, Massachusetts, New Hampshire, and Turkey. He earned his undergraduate degree in physics from Worcester Polytech Institute and his graduate degree in physics education from the University of Virginia. Dave is in his 24th year of teaching at St. Sebastian's and serves as the chair of the science department. He thanks his amazing wife, Holly, for supporting him in his calling to be a teacher at this school. Without further ado, I present to you Dave Wilbur, The Wave-Particle Duality of Light.
All right. Can you guys hear me? Yes. Awesome. Man, it is amazing to see so many of these faces popping up right now. I'm a little flooded, right? I'm not gonna lie, but I'm gonna power through here. Stay with me. First of all, I would like to offer a few thank yous. Number one, thanks to Mike Melly for making this happen. As I've told my students as we kind of entered this new realm, nobody signed up for this. SEBS is a school, built on interpersonal relationships, being in the room together, shared struggle together, and that's been a challenge in this new format. So I'm thrilled that Mike came up with this idea for us to have a forum where we could connect in one of the ways we're allowed to. So thank you for doing that, Mike. I got to thank Dennis Cleary and Chris Lynch. Their topics were awesome. I watched both talks, and I'm not going to lie, I'm not a history or an English guy, but it was outstanding. I can guarantee that had I had teachers like that in those subjects, I would have viewed them differently in my young career in a more positive and passionate light like I do now. I want to thank them for setting the bar so high that I should have no problem walking right under it in this presentation. And finally, I want to thank my fellow faculty, some of whom I can see are here. And the reason is for the inspiration they provide on a daily basis. So all joking aside about setting that bar high, the reality is, and I think everybody should know, when you walk down the halls, at SEBS as a faculty member, you can look left, you can look right. Doesn't matter where you look, you're just seeing awesome people doing an awesome job, and keeping the standard really high. And you don't want to let them down, let alone your students. So I appreciate that. Thank you. I'm going to dedicate this talk. I know it sounds weird to do that, but I feel the need to a few folks. Number one is my current AP class, AP Physics class, because we didn't get a chance to do this topic in school because of the COVID-19 situation. It's usually the last topic we do, and part of that's because there's a lot of foundation needed, so we can have a good discussion about it. But I'm really missing it because the questions that these guys ask are ridiculous. Like, I find myself staring at them blankly with no answer as often as not when we get to a topic like this, just because of the nature of the material, but also the quality of the question. Parents, I don't know how many parents are here, but I want to thank you as well. I wish, I wish that there were an easy way for you to get the classroom experience sometimes. And the reason I say that is because as a parent of myself now, I see things differently. And I realize, man, the trust you are putting in us, to send your son here and trust that we are challenging them, helping them grow, and setting, the proper atmosphere for that to happen. And finally, I want to thank the alums. Man, it's getting me right now to see all those faces. You guys are, why I showed up to work every day, and the guys now are why I still do. You bring the best out of me. You make my classroom fun, dynamic, and challenging, so that it's not just you that's growing, but me. So I'm dedicating this to all of y'all because you all, sort of influenced me. And I hope, especially my current class, you guys will jump in and annoy me at the end with some of your questions. Let me preface with a few things here. Real quick about what this talk isn't. I think it's important to lay that out. This is a big topic. And the goal is not to come out of here with a mastery of what light is and the nature of light. It's not going to happen, okay? And I don't say that to discourage anybody. Matter of fact, if anybody tells you they really know what light is, I would question them on that, right? I have a few questions for them. So please don't worry about that piece of it. Let's worry more about the forest, let's say, than the trees. That's kind of the analogy I want to use. Now, if there's a particular tree along the way, you want to have a question about, please send that over to Mike Melly, and he'll call on you later on, and you can ask me about that at the time. So then, what is the lecture about? It does have duality of light in the title. This is as much about light as it is about science. That wasn't my intent when I started to put it together, but that's where it went, and that's where my classroom often goes. So I think that's appropriate. So you may feel like, gee, this is a little bit more general about science than it is about specifically light. And I'm going to say, well, good, because I think that's important and part of what I'm trying to do. Finally, as it relates to style, again, there's not going to be the give and take, at least not early on like there normally is in my classroom. So that's going to be a little awkward for me, so bear with me. But what I'm going to do is I'm going to sort of insert an answer. So I'll ask a question every once in a while, and normally in my class, we would all pick sides. Who thinks this, who thinks that, and there will be some push-ups or some pull-ups on the line for the winners and the losers to have a little fun with it. But we can't do that. I mean, feel free to get up and do push-ups or pull-ups if you want in the middle of this. Yeah, I'm talking to you, alum. But I'm going to sort of fill in the gaps, all right, for now to get us through this. All right, so let me take a second here. I'm going to share my screen with you and open up my PowerPoint, and hopefully you'll see me alongside the PowerPoint. If you don't, feel free to do what Mike talked about. In the top right corner, you should have an option to change your view or to say something like show speaker or something like that. You may need to hit that. So give me a second. I'm going to switch over to my PowerPoint. All right. Real quick here. Going to check. All right, so I can't see everybody. I can see a few people. Is everybody able to see? Just give me a thumbs up if you can see my PowerPoint. Awesome. Thank you. That's what I needed. Okay. Let me move myself a little bit out of the way here. So what you're looking at on that screen, I'm not going to tell you. We'll come back to that. But there you go. There's your little tease right there. Okay, so hopefully everybody, when you signed up for this, signed the waiver. There was a health warning associated with this. You should have basically brought some kind of paper towel or something with you, so that when you experience some of it's natural. There's a brain melting going on during the process. So if stuff starts like oozing out of your ears, or whatever, don't worry about it. It happens all the time. Shouldn't be too uncomfortable. So just roll with it. All right. So simple question: what is light? Right? 3 words. What is light? What we're going to do to try to answer this question is we're going to go back in time a little bit to the mid-1600s. Now, obviously, we can go back farther than that or further than that. I guess that's not a distance. And look, the property of reflection of light is common, has been forever, right? If you look at a lake, a body of water, silver, any metal, glass, you can observe the reflection of light. So people have known about that for a long time. And another one is refraction of light, okay? So when light strikes something, sometimes it bounces off, but sometimes it goes through. And then, usually comes out the other side. And we call that refraction. And these phenomena were easy to observe, very common. But what wasn't easy was coming up with an explanation for it. So in the mid-1600s, Isaac Newton, arguably the greatest scientist ever, natural philosopher ever. Personally, I put him behind Einstein, but I could, hear an argument for it. He was one of the guys trying to find an answer to this question. And so he proposed a certain model to answer this question. Well, he had some contemporaries, very bright individuals as well. And one of those contemporaries was a gentleman named Christian Huygens, a Danish natural philosopher, scientist. And he had sort of a different opinion on what this might be, a different model. So what two models were out there? And I apologize, part of this is covered, but the two predominant models, right, were particle and wave. So Newton, for those of you that don't know, Newton was an unbelievable mathematician and scientist who created his own math when he needed it. He generated what are called Newton's three laws of motion, the law of universal gravitation. He just basically figured out how objects behave, right? Especially everyday object, if you want to put it in those terms. So marbles and bowling balls and, and light. Well, at least he tried. So he just had these amazing laws, and he took those laws and said, well, if they work for these objects, maybe they work for light. So I'm going to say that light is a particle, and that particle or those particles should behave according to my rules. And he may have to introduce a new force here or there to try to account for what's going on. And so on the left, you can see this is refraction. This is when light goes through one medium into another. And his model, explained it. Like he could say, hey, I can predict if it goes in at a certain angle what the next angle is going to be. Huygens, on the other hand, he had a wave concept for this. The idea that when there's a disturbance somewhere, that disturbance travels, and then we can track that as a wave, and that light's probably like a wave, and it would go through the substance, sort of like you see in that image there. So how do we settle debates in science, right? I mean, the most common method is, arm wrestling, sometimes taekwondo. But when those don't work, maybe we move on to sabers, maybe lightsabers, whatever it is. But ultimately, that doesn't get us anywhere. So in general, we settle for experiments and the results of those experiments. So the problem was that none of the experiments that they did at the time couldn't be explained by one of these two models, at least as they saw it. So there was no reason to pick one over the other than maybe your preference or a little, bits here or there. So the bad news is that it took 100 years, all right, after these guys. So let's say this was, sort of finishing up or at its best at like the end of the 1600s or 1700. It wasn't until 1801 that an experiment was brought forth, a very innocent, simple experiment that was brought forth that seemed to offer a chance to find the answer to the question of what, what's the nature of light? Is it a particle or is it a wave? So this experiment is this simple. The scientist who highlighted or brought it to the forefront was Thomas Young. This is called Young's double slit experiment. Those of you that are in my AP class this year who had me before will be familiar with this from our wave studies. And the question is simple. If I shine a light at a piece of cardboard or something like that, but I put a little bit of an opening in there, what am I going to see on my screen? We can all agree, right, that if I don't have any openings, I'm not going to see anything. But what if these openings are vertical slits or horizontal slits or just dots or holes? What am I going to get? Well, I'm probably going to get two slits on the other side or two dots on the other side. Well, if you do it, that's what you get. All right, there you go. And the particle theory says, well, that makes sense because if particles try to go through this, they're going to get blocked and they're going to end up here. Wave theory, could say, well, I guess the waves are going to go straight through and get to the other side. Okay, there were reasons they didn't love that, but they're like, well, I guess it could happen. So what do we do next? Well, we tweak the experiment. One way to tweak it is to make the openings larger. We made the openings larger, we got the same result. Another way, make the openings smaller. When we made the openings smaller, this is what we got. So this is not what anybody would expect out of the gate, okay? And so obviously they went back, they checked the experiment, they made sure that what they did seemed, clear in what it was doing and the variables it was testing. But there's a few, interesting things about this. Number one, obviously, there aren't two sources of light, right? There's not two things on our screen, two vertical slits or two dots or anything like that. In this particular one, you can argue there's 7. Second thing, all right, look at the middle. Okay, what's crazy, and I'm going to back up here a second, is this is exactly the experiment that was done. Well, in the middle of these two vertical slits is a blockage, right? Well, this brightest white spot is directly behind that. So not only did it apparently not block the light, but it created the brightest spot of all of the others, or the brightest vertical line of all the others. And then the third thing that stands out is obviously, well, this white light is here, but then here I'm getting a combo, and here I'm getting no white light. And so what is going on here? Well, if you do this experiment sort of more modern day, okay, with a laser, I just want to show you this because we do this in class together as a group, you get stuff that looks like this. All right, so basically we have the ability to make those slits really, really small. And I'll talk about how small later should we want to go there. But the bottom line is that doesn't even come close to resembling 2 dots, 2 vertical lines, anything like that. So the question is, can we explain this with each of those theories, those models that we had at the time, right, in 1800 basically? Well, the short answer for particles is no. If you shoot particles, pretty much you should see two vertical lines. Now there were discussions about was there some other weird stuff going on? Were the particles interacting with hitting each other and deflecting off at strange angles? Were they deflecting off the inside of the aperture and things like that? And those were legit questions, but they were ruled out as they went on, as they modified experiments and tried different things. Not all of them completely ruled out, but in general ruled out. But more importantly, when they decided, well, could the wave theory of light explain this? They got some interesting results. So what we're going to do right now is we're going to sort of use water as a model. Okay, so waves have a lot of things in common. Well, they share most everything in common. They have some differences. So if we study water waves, which all of us are pretty familiar with, we should be able to learn enough about waves to try to understand where the wave people are trying to make their case. So, simple thing, right? You can go to any water in the sink, water in the bathtub, water in a pond, and you can drop something into it, or you can poke it with your finger, and you're going to get ripples. All right, so these ripples will spread out, and you can do it, in a random fashion, or you can do it in a steady fashion, like, dip your finger in there like twice a second or 10 times a second, or whatever it is you want to do. So, this is a general behavior of waves. So how does a scientist, a mathematician, how do we represent that, and what terms do we need to move forward with that? So what I'm going to do here is, this is going to be the most technical slide I have today, hopefully. So bear with me. But what we do is we represent a wave in this fashion. So it repeats itself, right? So you can imagine that if I were to hit that surface of water at a nice interval, I'm going to keep getting, dips and then crests and then dips. So the terminology real quick here: crests, troughs, right? Crests are the high spots, troughs are the low spots. Amplitude is a generic quality physics term, okay? It's kind of an objective term that everybody can agree on. It simply means what's the maximum height or depth that my wave could get. And that's related to its energy, its intensity, right? With a water wave that the larger the wave is, the higher the crest, the kind of more dangerous it is, right? The more energy it carries. And that's what that represents. The other thing that's pretty obvious when you look at the diagram is, there's a distance, a physical distance from one crest to another, or one trough to another. And we call that the wavelength of that wave, right? No matter what kind of wave it is. This last one down here is important to point out. And we're going to skip some of the pieces that go along with it, but for now, look, the idea is if I compare a wave that looks like this to a wave that looks like this, some of the qualities are the same, right? We can argue that the amplitude or the height or the depth is the same in each of these. These two waves carry the same amount of energy I got to be careful with how I say that. Some people are going to come after me, which I would think they should. But each of these has the same amplitude. I'll keep it to that. But what they don't have in common is the frequency. In other words, if I were to put a sensor over here and count how many times per second a crest came by and struck my sensor, well, clearly I would get a higher rate of that in the upper one than I would in the lower one. And that's all we mean by frequency, okay? The frequency at which the crests will pass a given point every second. All right, hopefully that's all we need and we can work our way through the rest of this. So you saw in the previous picture here, this guy here, that if you were to drop an individual or even a bunch of individuals and you kind of freeze frame it at a certain point, well, they look like they're each doing their own thing. But if you let them continue to have their waves spread out, you can start to see things like this. And in wave theory, we call this interference, okay? One wave is interfering with the other. Now, it's an interesting word because it actually, in some ways, you could argue, doesn't interfere. And so here's what I mean by that. I'll just put a little of this in here. As the wave, let's say on the right, is being produced, I've got bright spots, which we can call the crests, the high parts, and dark spots, which we can call the troughs or the low spots. And you can see crest, trough, this wave is going to spread outward. Well, the same thing's going to happen to this guy on the left. All right, as the water is struck repeatedly, those waves are going to spread out. Well, at some point, they are going to meet. Now, when waves meet, it's interesting. They don't behave exactly the same way particles meet. And what I mean by that is if I send two marbles at each other, let's say in this direction, they hit, right? They are going to sort of reflect one another, right? Bounce off of one another and go off in a new direction in general. That doesn't happen with a wave. This wave here, if you were to follow this first bright ring and just follow it the whole time, when you got to a certain point out here, you could still be following it. In other words, he would have passed through other waves from this other source, but still go on his merry way. Okay, so does anything happen to him during the time, right? That's crazy. Well, yes and no. And what do I mean by that? Well, when waves occupy the same space at the same time, something particles can't do, right? I can't put two marbles in the same place at the same time. When waves do that, they do combine, okay? They appear to change and become something else. And for keeping it straightforward, there's two major types of categorizations of that. One is called constructive interference. And what that means is if one of those crests combines with another crest coming in, while they are in the same place at the same time, which they can do because they're waves, it will look like one larger wave. But right after that, they'll move on and go back to their original selves, seemingly unfazed, essentially. Now, destructive interference is cool because this is sort of the opposite of that. This is when a crest or one of the high points comes in and meets a trough. And they actually will appear to cancel out. They'll flatten. And, oh, we destroyed the wave, we think. Well, no, because if you wait a second, they'll pop out the other side and continue on with their lives as normal. So this interference property is something that Huygens said could happen and was observable in water waves. Particle theory had trouble explaining this, and we'll just leave it at that. Okay, another property that waves have that particles don't appear to have or didn't appear to have anyway is something called diffraction. And what this stands for is when waves come up to an obstacle. Now, keep in mind, I've only given one example here, but there's kind of two examples. There's more, but we'll just say two. One obstacle could be I could have in an ocean, right, near the beach, I could have rocks in the way. So I could have waves, run into the rocks, and then they would actually bend around the rocks and move on, okay? And that process is called diffraction. The other way that they diffract is when they go through openings. And you can see pretty clearly, right, the slide, I won't go back to it, but I misled you up front when I showed a slide of waves going into a barrier with a couple of holes in it, and then only two streams of waves coming out the other side, right? I did that for a reason. You can call me out on it later if you'd like. But in general, you can demonstrate that when nice straight waves come in, but actually they don't even have to be straight, but the waves come in, they get to this opening and they pass through, they don't stick to their lane, if you will. Let's see if I can show you this without shutting everything down, right? So if these guys were to stick with their lane, then you would only see these crests moving on. But clearly, you see something spreading out here. And that's what we call diffraction, right? That's one of the instances where that happens. Okay. So, obvious next question, right? Well, what happens when some of these guys cross over? Okay, in other words, we saw earlier that if I had, two things of water that I was hitting and they went through, they would kind of cross over each other. What happens if I do the same thing here and right next to him, I put another opening? All right, well, let's see what happens. Maybe. There we go. So, full disclosure, the picture I used earlier was a modified version of this where I got rid, well, somebody, I didn't do it, but I borrowed a slide where they got rid of all this other stuff that you would see in the right situation if the openings were small enough. So notice there's a source here generating a wave, and the waves are spreading out. They're diffracting. All right, waves are coming in, getting here, and just like this slide, they're spreading out. But right next to them, I put another one, such that every time that this long wave crest right here hits this opening, it sort of starts two new waves, each of them diffracting. But not only each of them diffracting, they're each going through the process at the same time, at the same rate, all right, same frequency, if you will. And they cross over each other. Well, when I first saw this diagram, I didn't know what I was looking at. I mean, this is, must have been high school. Maybe I don't remember high school and it was early college. But this took me a while to get my brain around. And we're not going to have time to get into it, but it's fascinating that this is what shows up. So what am I seeing, right? What are we seeing here? I'm going to take a step away from this for 1 second to show you a real world, like you could go out and do this version of this. And I was going to show the video, but I had trouble getting it to work the way I wanted. And rather than kick all of you out halfway through my talk, I figure I'll keep you here and just show you a still of it. So any of you young bucks, your alumni and current students, who actually some of the current students are those that introduced me to a YouTube channel called Veritasium. Phenomenal physicist, a great teacher. And he actually goes out to a little pond. And it's hard to see right here, but in his right hand, he has a ball. In his left hand, he has a ball. And all he does is take the two balls and move them up and down in the water at the same time. Now, the water has to be calm for you to get a clear picture of this, and he had calm water. And as he lets those waves spread and they start to cross through each other, look at this insane pattern. Okay, we did not, we don't see this every day. And I think that's part of the problem of why this is so phenomenal when we first come across it. And when, Thomas Young first saw this and others at the time, is like, wait a minute, we can make waves do this, and it's possible that if light's a wave, it could do this. All right, so that's what brings me to my next slide. Okay, that's the lie. Let's go back to that slide. I'm reminding you that that slide's important, right? What are we going to see? All right, now it brings me to my next slide. In physics class, this is how we would talk about this, right? I mean, there'd be some more math with this, but we'll avoid that. And notice, I have a source creating a wave. I have another source creating a wave. And if you follow these yellow lines, you will see that everywhere along them, a crest is hitting a crest, essentially. All right, it could be a trough hitting a trough, but let's just say crests are hitting crests. And that happens all the way along. And what do I see when that guy hits this wall? Well, I get a bright spot, right? Why? Well, because those crests have combined with crests to give me a nice bright light, if you will. Notice where it also happens. Right down the center. I have an obstacle right here blocking the wave. Okay, this stuff's being shut down right here. Yet, on the other side of it, directly behind that, I get a beautiful bright spot of light. And then I've got these dark spots. What's going on there? Well, if I recall, those crests can also combine with troughs under certain conditions And those conditions are met with the green lines. And so on the screen, what's happening is a crest from one wave is always arriving there when a trough from another one is. And so they're always canceling each other out, essentially. And I get a dark spot. So what's my point, right? What's the point of laying all this on you? It's straightforward. We had a question, is light a particle or is light a wave? Is there a model that sort of is going to win, right? That'll help us out? Yeah, the model's waves. So a couple of things about it. Number one, like, it ends the question. Okay, it turns out there's also another experiment. I'll mention it because it's kind of cool real quick. Newton's model predicted, or hypothesized basically, predicted that the particles, when they went through refraction, would have to speed up if they went from, say, air to glass and then back to, air to glass. Later on, when we had the capability to measure those speeds, we found out that it didn't. It actually slowed down. So that was another problem that was, with Newton's model of this, with his corpuscle model. But this is awesome news, okay? We have a clear evidence, strong evidence that any lab anywhere can do and repeat the experiment on their own, that the wave model of light explains this perfectly. And I can say, well, hey, what if I change the color from green to red? What if I sent in red light? Will I get the same pattern? Well, the theory says, yes, you will, except the pattern might have a different sort of spread of where the bright and dark spots are. And you can actually see that on this. It's a little hard, but you can sort of start to count how many green bright spots I'm getting versus how many red ones I'm getting, and see that there's clearly a difference, right? And when they overlay them down here, you can sort of see that the red ones seem to be a little farther apart where they're appearing. All right? And we're going to skip why that is right now, but that's just the way it is. And the wave theory predicts that that's what should happen, and it is what happens. So, great news, okay? My seminar's done. I started with the question, is light a particle? Is it a wave? What's the nature of light? Bam, it is a wave. Particle theory cannot handle that, and what's more, wave theory can handle anything particle theory can handle. And that's a sign of a good theory in science. When this theory can handle everything another one can and other things, well, then that's the superior theory, and that's the one we're going to go with, a superior model, if you want to say it that way. All right, but joke's on you. That's not the end of it. All right, and there's this sort of false sense of security again. Another 100 years goes by, essentially. All right, so now we're moving from 1800 to 1900, basically. And I want to talk about this for a second. This is my favorite part of physics. I never get tired of this for so many reasons that we won't even be able to cover today, but I'm going to try to get some of them out there. That is not what I want. Uh-oh. Oh, no. Okay. Never mind. Let me just talk. I thought I had a slide for this and I don't. Okay. What's going on at the end of the 19th century, basically, right? Late 1800s. Okay. We have Newton's laws of motion, laws of gravitation. These laws are tremendous at explaining almost all everyday macroscopic objects, marbles, bowling balls, cars, whatever you want to talk about. Okay, I don't know if they had cars yet. Anyway, all of those things, his laws were magnificent. Fluids, even things like that, magnificent at explaining this stuff. And then there was another theory out there. I didn't spend any time on it, but it was put together by a guy named James Clerk Maxwell, who gets not enough credit, in my opinion. But he basically took all of electricity and magnetism and waves, and he encompassed them in this beautiful 4 equations, essentially, that could allow you to, model anything in the real world and make predictions. These 2 theories were so powerful that they were explaining almost everything at the end of the 19th. And I refer to these things as dangling chads. There were like, 5, 6, 7 experiments out there where, well, the models weren't quite getting it done, but we'll figure it out. Don't worry. I mean, we've come this far. There's something we're not doing right with our experiment, or we're not quite thinking the right way on this, or there's some tweaking to be done. And I'm gonna not be fair to those scientists in the sense that I can imagine that some of them felt like, man, we really have this under control. We really know what we're talking about. And we'll handle the dangling chads later. Okay, well, one of those dangling chads was an experiment called the photoelectric effect. It was performed, I believe, first by Heinrich Hertz in late 1887. And I don't know the details around sort of how he went about his business, but I'm going to present it to you in a certain way, hopefully to kind of to pull you in and mislead you just enough to get you where I want you. So let me try to explain the experiment. It actually is really relatively simple, but since we haven't talked about some of the stuff going into it, you may have to just roll with me and stick with the forest while we talk about some of this. Okay, I took this screenshot from a website that we use a fair amount for experiments that we don't have the material for to reproduce in class, or we just don't want to for various reasons. It's called PhET. It's University of Colorado. I want to give them credit because they do a great job. So what is the experiment? I have two metal plates here. We call them parallel plates, but they're just metal plates. They're hooked up to a little bit of a voltage here, and the voltage is just serving to help kind of get these electrons from one plate to another that might appear when we do our experiment. And then I have a device here that measures how many electrons per second, essentially, are reaching the other side. So Hertz and others, right, would say, okay, let's do this experiment, and we're going to predict what's going to happen. So I'm going to send in my light wave. My light wave is going to strike this surface, and my light wave carries energy. And so, there's chances that that energy is going to hit an electron, give that electron the energy it had, and that electron will escape the metal and float across to this other plate where we'll detect him. So the gist of it is pretty simple. I'm going to shine light here. Some particles are going to get kicked off, and I'm going to measure two things: how many are getting kicked off every second and how much energy they have. Those are kind of the two things we care about. Okay, wave theory, straightforward. Let's go back to our little mini diagram I have tucked in the right corner here. Wave theory says basically that each of these crests, okay, is an opportunity to sort of interact with an electron or hit an electron and give the electron that energy and send the electron out from the piece of metal across on its journey. So wave theory predicts that if I have a high frequency, okay, a high frequency wave go in, like purple or blue light, that I'm going to kick off a bunch of electrons, right? Because each time a crest hits, it's going to have a chance to kick off an electron. Whereas low frequency light is going to kick off fewer. And if I want to mess with the energy of the electrons, I leave the frequency the same, but I'll increase the amplitude, right? That way, the electrons get hit at the same rate they were hitting at before, but they'll have more energy when they come off because the wave gave them more energy. Okay, so they do the experiment, all right? Guess what they find? None of those things happen. None. What's worse, the opposite basically happens. So what do you think they do, right? What does a scientist do? I mean, they probably cry a little bit. Then they chastise themselves and say, there's something wrong with my experiment. So they go back, they check everything, they tweak it, they talk with colleagues, they run it by colleagues with their procedure, they check their equipment, like they do everything, right? They have other people check their stuff, they send them their papers, hey, check my work and my predictions right, which again is one of the amazing beauties of science and engineering. And so he does all of that, right? And everybody seems to pretty much agree, like, yeah, like your predictions are right. And he said, and then he says, well, do it yourself, build it. Here's my device, build it in your own lab, do the test. They do the test, they get his results again. Okay, so I want to be clear about this. This is only one of the dangling chads that we're about to walk down. It turns out there were a few others going on at the time, all right? But let's follow this one sort of down its rabbit hole. All right, so where is this going to bring us? Well, it's going to bring us here, all right, to this relative nobody. There was another experiment at the time that went on. I kind of skipped it. I'll touch on it here now, called black body radiation. And what does that mean? Basically means that when you heat up something, that something glows, and it releases certain colors when it glows. Well, if you graph what that's supposed to look like, you get a certain graph. Okay, here we go. Hey, let's use our wave theory to explain the graph. Well, we couldn't. Okay, we could explain part of the graph, but not the other part of the graph, and then we could rearrange how we thought about it and explain the other part of the graph, but not the one part of the graph, but we couldn't get it all together. And a mathematician / scientist at the time, Max Planck, he just decided, and I love this move. I love this move because I hope it gives students the permission they need to do the things you sometimes have to do in math and science and engineering, which is step outside the box. And what Planck did was, he was really good at math. And he said, well, look, if I make this certain assumption about how light behaves, I can explain this. I shouldn't say that. I can't explain it, but I can give you the graph. I can model it with that assumption. And his assumption was, well, what if I just act like light isn't a wave, but it comes in these little sort of packets of energy? And the packets of energy, they have energy related to their frequency, right? Not their amplitude. I don't know if he liked it or not. I haven't read a biography on him well enough to know. But he admitted that, I think that he didn't believe it. Something along those lines, right? But it didn't stop him from using it. Why? Well, because it got the model. It fit the model. All right, so he's out there doing his thing. Others are looking at his work saying, well, that's cool, but that's not really working because it's, that's not a wave model and waves are the right model. But along comes Einstein. And there are many reasons, in my opinion, he's the greatest, physicist ever. One of those reasons is because Einstein had the ability and the willingness, as much as and maybe more than a lot of other scientists, to simply accept, well, maybe something's true that I don't think is true, right? Or I'll say it differently. The results of the experiment are the results of the experiment, okay? I don't have to like it, okay? And we can all do the experiment and we get this result. So let's take what Planck did to solve it, and even if we don't believe it's right, let's use his model and take a look at the photoelectric effect. He said, right or not, let's take and use the model and see what happens. All right, so what does happen, right? What happens here? So let's revisit the picture. Now in the bottom right corner, I'm giving you some, who knows what a photon looks like, idea of what a photon looks like. Let's keep it relatively simple for now. And say that photon that light, rather than being a wave, right, and traveling and doing this thing as a wave, maybe is a bunch of small pieces of light or particles of light, which later gained the name photon. I think it was in the 1920s that it gained that name. But let's just imagine that instead of it being a wave, it's particles. So would that change our predictions? And how would that match up with the experiment? So I want to walk through that just a tad, all right, and see what happens with that. So situation one, Planck said that the energy of this incoming light was actually tied to the frequency of the light, okay? And what that meant to him was that if I send in light that's higher up this rainbow into the blues and the purples, they're going to have more energy. And therefore, when they kick off an electron, that electron's going to have more energy. So when I increase the intensity of that light, it should do that. All right. But how do I increase the intensity? Or I should say it differently. I got to be careful with that. I knew this was going to happen. If I increase the frequency, if I change the color, all right, the prediction is with particle theory, I'm going to get them kicked off with more energy. Okay. Doesn't make sense to wave people, but whatever. The second thing he had to deal with was, well, what does it mean to make my purple light more intense, right? Like you all know that when you're seeing some purple light or something and it's kind of light and then it's, more intense, maybe a deeper hue, you could say it that way. What does that mean in terms of these particles? Well, the explanation was that means that there are more particles per second passing a given point. You could say the particles are maybe more dense as they're passing through the air. So what does that mean for this experiment? Well, this means that when I send in the same purple light, but just make it more intense, I have more particles striking, but they don't have any more energy, which means I should get kicked off of here more electrons, but without any more energy. And guess what happens? Both of those things happen. Matter of fact, they could predict what the values of the energy should be based on the light they were sending in. And they could predict the current and how many charges per second were going to show up on the other side. And there were other things that I'm not covering that were a result of this experiment that wave theory couldn't even come close to predicting, but the particle theory predicted. Okay, so what I would like to do is just go back to a screen view here. Let's see if I can do that. Are folks seeing me still? Awesome. Okay. So I'm not going to reference those diagrams anymore, but at least not visually, but I may reference them otherwise. Where are we at? Okay, where does this leave us? I have an experiment, simple, double slit. Send light at it. I get a wacko picture on the other side. Okay, particles, can't explain it. Wave theory matches up amazingly. 1900, I've got an experiment, photoelectric effect. This particle or quantum theory or quanta theory that Planck throws out there and Einstein sort of uses and champions at a certain level explains this, but maybe not other things. So we step into class and we say, hey, Mr. Physics teacher, what's the nature of light? Okay, is it a wave or a particle? And their answer to you is yes. I hate that answer. I never liked that answer. Okay, why? Well, mostly because I'm probably not smart enough to handle that answer. But let me talk about it a little bit more. Let me put a little bit different spin on it. Let me give you a scenario, right? You're going to take your son or your daughter to get a used car, right? 17th, 18th birthday, whatever. You're going, let's go. You got to drive yourself. I can't do this anymore. Okay. You ask the car dealer, hey, is this car safe or not? And he's like, oh yeah, definitely. That's not an acceptable answer, right? You go to the doctor says to you, oh, you have chest pain or not? Yeah, definitely. That is not helpful. Okay, well, as crappy as that analogy might be to a physicist or a scientist or someone else listening to me right now, I like it because it's the slap in the face we might need to sort of start to come to grips with this. Is light a particle or is light a wave? Yes. And it gets worse than that. I'm going to kind of stop it there, all right? And maybe some folks will ask me some questions that force me to go down a little bit of another path that I'm probably even less qualified to talk about than this. But this is an opportunity for physics to fail, to break. Okay, what they're basically saying is we don't know what we're talking about, okay? I can tell you that there's an explanation for the double slit experiment and tell you that light's a wave and it behaves like a wave, but then you go to use that over here and it fails. And I can tell you the other way around. So, the question is, do you really know anything? Like, what's going on here? Ironically, Einstein was one of the, the least favorite of this going down this path. A famous statement of his, God does not play dice with the universe. Now, I want to be clear about that for a lot of reasons, but let me be clear about it. Einstein had no problem with the data. Okay, we have to be clear about that. He's not saying there's something wrong with the data. What he's saying is the explanations that we are starting to be forced to consider to explain the data are not palatable to him, at least not out of the gate. He's holding out this hope that, no, this concept of I'm going to have to accept that the answer is yes. I don't like that. Okay, but that's okay. All right, that's okay. But he's not denying the data, and that's, I think, what's extremely important to point out here. So what happens at this point, right? I mean, physics could start to fail. I mean, don't get me wrong. I'm being extreme about it. Clearly, in certain situations, I can treat light as a wave and do my thing, and I can treat it as a particle in others, and I can do my thing. But we would really like to have an all-encompassing model or theory that, kind of makes this all work. And what happens at this point, and I love this because AP students that are in my class now, alums that are out there, okay, the folks that figured out how to wrap their head around, or not even wrap their head around it, just accept it and move forward, were mostly the young physicists of the day. Now, we can debate why that is, okay? And I would submit that, like me, I'm an old fogey and I start to get stuck in my ways, and this explanation works for me, darn it, and this is going to be, what I use. I'm going to fit the reality into my box. But the younger ones, okay, they had less of an issue. They were more willing to say, is it a particle or a wave? Yes. Now, let me put that in a mathematical formula for you, right? I'm going to give you Schrodinger's equation in a... Wally's going to kill me for this. I think he's in on here, and some other will probably kill me for this. But basically, hey, there's a probability, there's a chance it's a particle. plus there's a chance it's a wave. That equals 1. In other words, I'm 100% sure that it's one of them. And that is the beginning of quantum mechanics, quantum physics. Right? I mean, I don't know. I don't know that I came to grips with that in my own college days when I had to do problems with this and act like I knew what I was doing. The fact that these young scientists at the time were willing to say, well, hey, I love you, Einstein. You're the man, okay? But I'm willing to take this step. We're going to start taking this step. And Einstein, of course, I mean, as much as he fought it and others might have fought it, and again, I say that term loosely, he fought it, they went kicking and screaming. And good for them, right? We shouldn't give up on the stuff we've got that's gotten us to this point. All the developments, the models that have worked for us, all the technology we've developed based on those models, we shouldn't give up on those. But this forced a change in thinking. Full disclosure, I knew I was limited as a physicist at some point. Go ahead and laugh at me, Gus, if you were out there, all right, and others. When we started entering this probability stuff, my brain starts to shut down on some of this stuff because it gets weirder. Okay, but here's the thing. There's two, maybe there's more, what do I want to call them, camps when it comes to quantum and dealing with quantum. One camp says, I don't really care if I understand every piece along the way. I don't really care if I can visualize what that equation means to me or what part of that equation means to me right now or a result along the way. What does that mean in the real world? If out the other end, I get something that means something and something that I can use and something that explains what I'm seeing and allows me to predict new things. Yeah, I was bad I was bad at that. I was not in that camp. I was in the other camp, which is, well, this stuff has to mean something. It has to mean something in the real world that I can comprehend. And so that's where I sort of kept beating my head against the wall. I have grown a little bit, but not enough to fully, get where I need to be on this. But you could say, well, is the new model, this quantum mechanical model, does it do anything for us? And the short answer is yes. All right. I got one word for you: computers. Okay. Computers are a quantum-based product, technology. All right. Goes down to transistors, semiconductors, microprocessors, right? At least certain type of computers. And there's others: MRIs, lasers, LEDs. All of this stuff is founded in some aspect of quantum mechanics that we would not otherwise have been able to predict was possible, all right, without it. So I'm going to end here in a minute. I've tried to keep this focused on, the duality of light. There's a whole bunch of other things we could go down that are, crazy, amazing, just like this, that interestingly most kind of meld in with quantum mechanics, but not all. That's another cool discussion. But I do want to say one word, and it's going to seem out of place, but I'm going to say it anyway, about our current COVID-19 situation. And the reason I'm bringing it up is there's a lot of talk about, modeling. And the modeling, there's various kinds of modeling. And if you want, somebody can say, hey, Mr. Wilbur, we'll talk about it a little more. But I'm just going to leave it at this. Scientists take the facts and try to match math to those facts so that we can make predictions. All right. It is not a perfect thing all the time because there can be multiple variables within there that have different influences on the situation. And some of those variables are complicated, such as, human behavior. Okay. When you're making a model that's trying to account for something that you don't reproduce in the lab, well, then how do you model that, right? And it's not a perfect science, but I do want to say it is powerful. And again, I can talk more about something like that later on, but I do hope folks come away from this talk with a little bit of something that's, even if the whole light thing is darkness to you, as it is to me at times, that there's a piece there that you can carry forward with you as you sort of absorb the information that's out there and coming your way through this process. So with that, I'm gonna stop my talk and turn things over to Mike Melly and open it up to questions. Again, thank you all for your attention and for showing up and listening to me talk about something that I'm probably 2/3 qualified to talk about.
Dave, thank you very much. That was outstanding. We actually do have some questions lined up for you. And the first one comes from a colleague, Richard Palmacio. Richard, would you unmute yourself and join the conversation?
Oh boy, here we go.
Let me see. Did we lose Richard? Hold on one second. Richard, I'm going to unmute you. Fire when ready. You good?
You hear me now?
Yes, sir.
Yep.
This was a fantastic explanation, and I really enjoyed your discussion on the double slit experiment. I understand that if you emit one photon at a time to a double slit apparatus, it still creates the interference pattern. Yet when you put a detector at one slit to see which one it went through, it behaves like a particle. Is this part of the duality situation that you explained?
It is. That would have been, great question. Thank you for that, Richard. That would have been sort of where I would have gone next had I sort of wanted to push the limits of brain melting. But yeah, Richard Feynman actually is one of the reasons he's famous as a scientist in the mid-1900s is that he did a lot of experiments with this. He actually tried to put photons, right, which we are sort of claiming are these particles of light, through tests. And one of the tests was, I'm going to send this through a single opening. I'm going to send the photon through a single opening and see what I get. Then I'm going to send it through, shoot a beam of photons at a single opening. I'm going to send a beam at double opening and see what I get. And again, if I understand it correctly, when he sent them at a single opening, he pretty much got a single bright spot. When he sent it at the double, he got interference pattern. So then, to your point, he tried to trick it, okay? And one of the experiments that they did was exactly what you said. They actually put a sensor in to try to see, before the photon got to the double slit, whether it was actually a particle or a wave. And it turns out that when he did that, it ended up exhibiting particle behavior again. So I don't want to go too far down this path, number one, because my knowledge is limited on the range of the experiments and all the exact details. But it brings up a larger point, what I want to thank you for bringing up, which is, I asked the question, well, hey, is light a particle or a wave? And the answer is yes. Well, you could ask the question, is a photon actually a particle or a wave? You can actually ask the question, is an electron a particle or a wave? And I don't ask these, well, right now I'm asking them in a kind of a vacuum, but physicists didn't ask these questions in a vacuum. As soon as you had to admit that light sort of seemed to exhibit both properties, then you had to start to admit that maybe particles exhibit those properties, like electrons, and maybe particles of light that we claim are particles are exhibiting those properties. And so to take like maybe a little bit one step higher in this discussion, you physicists, what they are really doing when they make Schrodinger's equation and quantum equations, they're basically saying, look, it is everything at the same time and possibly nothing at the same time. That last part might not be true, but the idea is, it is a particle. Is it a particle? Yes. Is it a wave? Yes. Is it both? Yes. I don't know if it's neither is allowed. Someone have to check that on me. But the point is, if you put in the probability of what it is possibly going to be, and that probability ends up being 1, what do you call that thing? What is that thing? So anyway, the point is they learned that when they tried to watch what was happening, to sneak a peek on these photons and on electrons and other things, it seemed like it, this is going to sound horrible, kind of knew they were watching. And its behavior would change, the photon's behavior would change based on whether they were watching it or not. All right, what does that mean we're watching it? Let's be careful about that. We can't see it, right? We, not in the sense of can see a marble, can see a photon or see an electron, but we can put sensors in that can detect them. Well, what does that mean? Well, it means that you then have to send something at that particle or that photon or that electron to detect it. Well, what might you have done if you sent in something to interact with it? You might have changed it, right? You interacted with it. You may have now changed what it is or how it's going to behave. And that was a massive eye-opener to physicists, that our observation of the situation could influence the outcome. Now, It sounds really nebulous and crazy, but it's not when you start to think about when we say we're going to watch it or look at it, it means we're going to send some stuff at it, and that stuff might have hit it. And so we get some information back, but then we lost some information or things may have changed. So yes, what you said, Mr. Camacho, is true. And there are other versions of that where they try to not observe it, but trick it. For instance, one of them was, I'm going to send it such that it has to be going to, say, the slit on the right, but then I'm going to shut that slit, supposedly before it gets there. What's it going to do? Well, does it go through the other slit? And yes. And how does it go through? What does it look like? So there's a bunch of experiments, and Feynman really worked hard on this. And physicists are still doing these experiments today. They're still running experiments to try to get closer and closer and closer to a better understanding of what is a photon, what is an electron, what is light. So I apologize for the long answer, but all of those pieces are kind of related to that. Thank you for that.
Great question, Richard. Dave, I have another question from the field. Could you share with us some of the other dangling chads that you mentioned?
Okay, I'll give you the short version.
Maybe one or two.
Yeah, so we already hit one of them. Okay, so photoelectric effect was a dangling chad. Okay, the black body radiation, whatever that was, that I didn't really explain, was a dangling chad. The huge one was the atom. This is my favorite other one. Around this same time, a scientist, physicist named J.J. Thomson, did a seemingly innocuous experiment. He basically put gas in in some glass, put some plates on the other side, and tried to use some electricity to make something happen. That's the short version of it. When he put some pressure or electric pressure on the system, all of a sudden a beam of particles, or the remnants, or I'll just say a beam of particles was created. And he's like, whoa, where did those come from? I only had a certain thing in the glass. There was nothing else there. And we know atoms are indestructible. So where did this thing come from? And they had looked at it, where did it come from? Well, they realized later on that he broke an atom. He ripped something out of an atom. Now, we call that an electron. Okay, I think he called it a cation or something like that at the time, but it was an electron. And so they realized that atoms were breakable. And that opened up a whole can of worms, which is arguably, my second favorite topic. But the funny thing is, it's within this same topic of modern physics with all these dangling chads. So that was another big piece to that. Radioactivity was another one where it's sort of like, why is this seemingly so complicated? It shouldn't be this complicated. What's going on? Turns out that radioactive materials are exhibiting quantum behaviors with things sort of escaping. I'm not going to get into it, but that was another one that was going on at the time. And then there were some other experiments along the way. But another, I don't know if I'm going to call this dangling chad, but Einstein, at the same time as he was sort of answering and dealing with this photoelectric effect thing, was, answering other things like Brownian motion and special relativity and general relativity, these other ridiculously, massively influential, paradigm-changing things. And again, I'm oversimplifying it, but to me, I got 6 or 7 things left I can't explain. I'll get to it. We're almost there. And then the unraveling of that is almost the unraveling of physics. But it's not, because it leads to quantum, which leads us to where we are today. I will say this related to that and why I'm also fascinated by it. I could argue, and some if there's some professors on here, they might fight back with me on this, and that's fine, that we are maybe in a little bit of a place like that again. In other words, there's tremendous, and deservedly so, tremendous trust in some of the various theories and models we use right now. Okay, general relativity, Einstein's relativity, is amazing at predicting events, the way certain things should behave. The standard model in quantum physics, tremendous, right? So there are these things that are out there that are so powerful, and we rightfully trust so much. But I feel like 100 years ago, 120 years ago, maybe they felt the same way. Now, I'm not saying stuff's about to unravel, okay? Do not quote me on that. But I am saying that the humility that got built into physics, and all sciences really, the humility is its greatest strength. Right? And that had to be demonstrated back in 1900s, early 1900s. You had to face the fact that these these facts were facts. You don't have to like it, but they are what they are. Okay, now you can then work on the model and debate all that stuff, but the facts are the facts. And they eventually did that. Okay, and I wonder if there's something like that still to happen. JR, you could correct me. I think I've heard this from you, or we shared it, but I don't know if it was Neil deGrasse Tyson or some modern physicist or astrophysicist said something like, we think we understand 4% of the known information in astronomy or in the world, in the area of science or something like that, which is not very much, but we understand that 4% really well, right? Which, hey, if that's true, I love it, because you are really confident in what you know and attacking with it, but you're also humble enough to know that, yeah, that's still a small fraction of what there probably is to know out there. Thanks for the question.
Dave, we have one more question just to talk about it. How would you describe something that's, you kind of alluded to it a little bit in your last question, so I'm trying to paraphrase this a little bit, something that is on the cutting edge of physics laws and where there's a lot of debate? What topics on the edge of physics right now are attracting a lot of debate and attention?
You know what? I don't know that I know. I'll be honest. I probably do if you say it to me. Yeah. I guess I think the current one might be quantum computing.
Okay.
Maybe artificial intelligence related stuff to that, but quantum computing is probably that. The concept of what's called quantum entanglement. Crazy stuff that if I even open my mouth too much, right, I'm going to know I've crossed over to a path I shouldn't cross. But the concept of, and again, this is where it gets so amazing, that particles, subatomic particles, let's be clear. And by the way, let's be clear about all of this. Most of this discussion is about subatomic particles we can't directly see. But these subatomic particles have the ability to, for lack of a better word, phrase, know what each other is doing. Quantum entanglement is that's what I kind of understand that it is. Again, I'm not an expert on it, but it's fascinating because this is now being used to do experiments to try to gain insight into the nature of light and photons and particles by taking advantage of this idea that if these two things are entangled and I send one off to do something, well, when something happens to that one or the other one, I immediately know the status of the other one. And not only that, the other one knows its new status and what it has to be. And I don't know if this is correct or not, but I've heard that stuff can happen at supposedly faster than the speed of light. Maybe that's wrong, but if that's true, say what? Like what? Okay, so that to me is one of those areas. Quantum entanglement, that kind of idea would be one of those for me.
Well, Dave, I think you've successfully melted a few brains in the crowd with that last comment. So
I hope it was mild.
It was awesome. I want to open the room up one more moment. If anybody would like to chime in, Bill Burke, I saw you there. Thought you might be interested in chiming in.
You might need to unmute himself.
Yeah, I'm going to try that for him.
Bill, you need to unmute.
Let me. Bill, there you go, Bill. You're unmuted.
I'm unplugged.
There you go.
There we go. Hi, Bill.
David, thank you so much. That was wonderful. I loved everything you said. That you work really hard to know what you can know, and at the end of the day, we're pretty humble. If we're honest, we're humble because there's so much you can't know. The old line, the greater the island of knowledge, the greater the shoreline of wonder. It just you get locked on something, and then. And you're thinking you're locked on something, and then you find out you were wrong all along. So I just loved it. And to be able to hold two different theories in one's mind at the same time and not have your brain melt is a in of itself. So thank you so much.
You're welcome. Thank you, Bill.
Well, I will call tonight to a close. I'll say, Dave, thank you very, very much. This has been fascinating and informative and dynamic. Now I know why everybody enjoys your physics classes over the years. And I would invite everybody to keep an eye out for one more speaker series that we have next week, Aquinas, Morality and Happiness, hosted by Dr. Ryan Patrico, our religion teacher. And welcome to everybody tonight. and have a great night. Dave, thank you so much.
Thank you, Mike. Thank you, everybody. It's
you.
phenomenal to see all y'all. I see you out there, Angelico, Osh, Barnard. Oh, yeah, I see y'all. Thank you so much for showing up and listening to me ramble on and make me a little bit nostalgic. Take care, and don't be afraid to reach out.
I love the guy.
Nice job, Mr. Wilbur. Thank you.
Thank you very much.
Good job.
It's awesome. Chatting in, I guess.
Thank you.
I see that, Jimmy.
It's cute.
Hey, there you are.
I don't know who
Nice. Lunch. All right.
Okay, we can put
Thank
you
you.
You're welcome, Teddy. Dylan, good to see you, Teddy. Gus, there he is.
Oh, I think our mic is on.
Hey, Gus. Is he gone? I want to know how many things. Gus, how much did I get wrong?
No, I think I got everything.
Yes.
I don't really remember.
Right.
It's been a while.
It's been a while for you. It's been a while for me, my man.
But yeah, I want to come visit Stu.
Yeah.
Hey, when we're allowed back in, man, you got to visit me.
Yeah, definitely.
Hey, Mr. Wilbur, I heard we got a machine
How long was I slated up?
I'm sorry, I got a couple saying. Was it Barnard? What were you saying?
machine shop, I heard.
Well, I'll be honest. It's we have 2 innovation spaces, one of which is, yes, partial machine shop. So you did not hear that wrong. Bandsaw, drill press, oh my God, CNC mill. That's the guy, and I can assure you, not a single one of us knows how to use it yet.
Great.
But we bought it because if you don't buy it, you'll never learn how to use it.
That's exactly right.
Exactly. You know how that is. All right, I'm gonna check out. Thank you so much. It's great to see all y'all, faculty as well as alum and current students. Take care of yourselves and be in touch. Okay.
Thanks, Mr. Wilbur.
Yeah.
Great.
All right.
Have a good night.
Thank you.